Chemical Engineering, Polymer Science 757, Polymer Rheology, Professor H.H. Winter, Lecture 5A. We started to talk about the stress tensor, which defines the forces which are locally transmitted in a material. And for doing that, we do a little area element, dA, into the material, and that element had the normal N. So with that configuration, we define the force transmitted through that area element would be dF. And if you divide this force by the area, dF divided by dA, that would be the traction. And we would have to take the limit of a very small area element. And I redrew this here as a schematic. This is our area element with a normal. And this is the traction, the force per unit area transmitted. The dimension of that traction is Newton per square meter, or is equal to Pascal. PA is standing for Pascal. The stress locally is defined by the stress tensor, which allows us to pick any, if we know the stress tensor, then we are allowed to pick any n, any direction of our infinitesimal area element, and we can calculate the associated traction transmitted through. And remember, we needed 3 of those tractions, or 3 area elements at point P to have a complete description of the stress, to have all components of the stress tensor. The sign convention would be the following. If this traction is pulling on the surface, then we would talk about a positive stress, a positive traction. Or if this traction vector would be pushing on this surface, then we would talk about a negative traction or a negative stress in this case. Let's talk about some properties of the stress tensor. The first important property is this fact that the stress tensor is symmetric. That means the stress tensor components Pij are equal to Pji. You can interchange the components. That also means that you could write the stress tensor, or that you could write the traction here as n dot pi or at pi dot n. It doesn't matter because of the symmetry of the stress tensor, which is kind of nice. We can be a little bit sloppy in writing those components. Now, that has to be proven somehow, that the stress tensor is symmetric and comes out of the conservation of angular momentum for a material element. Now, we assume that on a little area element, that only shear stress is transmitted on those surfaces, but that there is no couple stress. And for documenting a couple stress, I documented a material element, say in a liquid crystal polymer, maybe a stiff molecule, where a couple is acting outside and then a counterpart is acting on this side. So to document this, like if I would bend this stick, if I introduce a couple on one side, another couple is seen as a response. And in the same sense, for this material element, there would be a couple stress in here. And the same phenomenon might occur in fiber suspensions. Nobody really could pin down that question experimentally. Theoretically, people looked at the consequences of couple stresses transmitted. And one consequence would be that this stress tensor is non-symmetric. Okay? So in the following, we will assume that this is symmetric. Couple stresses will be neglected. And if we do that, we can draw a volume element of arbitrary shape and size around a point P, and then could connect this point P with a surface element, ds, by using just this vector r. This would be just a connector vector. And on the surface element, there's a traction, which we just described. That's n times the stress tensor. So this traction, then multiplied into r, would give us the torque due to the little surface element ds. So that's the incremental torque for that little element. And if we integrate now the torque over the entire surface, this would be a double integral over the surface area, then the result would be equal to 0. If there would be a torque, if this integral would be finite, then the material element would start accelerate, and so if we have no angular acceleration in the system, also if we have no body forces which cause some torque in that system, then this integral has to be equal to 0. The traction can be replaced by n dot p, stress tensor, as we did before. And then with the Gauss theorem, we can convert the double integral for the surface into a triple integral for the volume. I will write down the Gauss theorem a little bit later. So we reduce this into a volume integral. And then we realize that the shape of this element can be really arbitrary. We could choose another element around our point P, and if the integral has to be 0, then this will require that the kernel of this integral is equal to 0, just due to the arbitrariness of the shape. So this kernel, this function, has to be 0 in the vicinity of point P, and when you go through all the details, then you will find that the stress tensor has to be symmetric to satisfy this condition. And you can do that as an exercise. I'm not going to to explore that further. Okay. Now I want to discuss the stress tensor with you in terms of geometry. You can describe the stress tensor in abstract mathematical terms, but there is a geometrical meaning of the stress tensor, and let's go through that in some detail. The traction vector can be drawn locally at point P as the product of n times P, and in the following we will assume that we know the stress tensor P, that this is fully defined, and that we are just varying this normal vector in. We want to see what's the stress as we are tilting this surface, this little area element, and then what would be the associated traction. And it turns out that the traction is following a ellipsoidal figure. And I have to prove that to you. But in the moment, let's accept that the traction vector is just drawing an ellipsoid in space, and it's called the stress ellipsoid. So if you know P, we can draw this ellipsoid. And we can evaluate this ellipsoid now. It has a longest axis, say this one in this direction. And for this special case here, has this longest, second longest, and third longest. Has 3 axes which characterize this stress. And if you recall that 3 independent traction on 3 independent material vectors are sufficient to describe the stress tensor, then you could say that if we know this traction, that traction, and this traction with their associated area elements, then we have a complete description of pi. So that is a complete set. It's complete information for defining the stress tensor. Okay, now let's draw this area element in here, which is associated with the traction going along the longest axis. And it turns out that this area element, it's a principal plane, is in the cross-section of the ellipsoid, and the second and the third principal stress are lying in that plane. And the normal to this plane is going into the direction of this axis. That can be also proven in detail mathematically. So what I want to say is, if we look at a traction in the principal direction here, then we also define a material surface which is normal to that traction, or n, in other words, n goes in the same direction as the traction vector. And you can do this for all 3 surfaces You have three principal planes and three principal stresses. And when choosing now a coordinate system which goes along this axis, that axis, and this axis, this coordinate system would be a principal coordinate system. Then you would get the components of a stress tensor only on the diagonal, off-diagonal terms would be eliminated. And those are the principal stresses. So this is the geometrical meaning of the principal stresses. Let's push that concept a little bit further. Let's just look at a figure. Let's start here with the lower part of this overhead. And let's analyze the traction in the first principal direction, t with a super 1, I used here with this notation. And there is the normal vector, which is associated with the first principal plane. You have the text, but this drawing I just put in a few minutes ago, so you have to bear with me. So just look at this configuration here. N is collinear with the principal stress in one direction. And we can write this down now. We could say the traction in this first direction would be n times p, or p times n, doesn't matter. And n would be the first normal vector, would be a principal unit normal. And this vector, this traction vector, is just equal to n times some factor which stretches n. And this factor is lambda. Okay? So n and pi are collinear, and n is just stretched to produce the first stress. Now, in general terms, now this is a new handout which I gave you. In general terms, you could say now that n times p minus lambda times n is equal to 0. In the special case that n is collinear with the principal direction. If n is pointing in any other direction, then this equation is not satisfied. So this equation defines the three principal directions, giving us the three n's. And it also defines the three stretchers, if you remember that we are stretching n into the length into the principal stress. So lambda is giving us the stretch, and lambda 1 is equal to the first principal stress, lambda 2 second principal stress, and lambda 3 the third principal stress. And the associated normal vectors here would be the base vectors for a coordinate system, and we would call this the principal coordinate system. Okay? So that's the geometrical meaning of the principal stresses and the stress ellipsoid. To evaluate this equation as sometimes very involved, you would first take the determinant of this first expression here of this tensor, and this would have three solutions, would give you the three lambdas, and with the three lambdas, you would find out what the three n's are. Okay. Now, I would like to show that we really talk about an ellipsoid, that the stress is going through, is following an ellipsoid when, lost here my microphone, when the traction is moving around. So in this case, I put the three principal axes here, x, y, and z. We are operating already in a principal coordinate system. It doesn't matter whether we use the stress matrix in the principal coordinate system or not, because they are fully defined by the three principal stresses and three principal directions. So we can choose just our three axes like this, and we can choose an area element like this with a normal n, and as this is rotating, t is now moving around this ellipsoid. Now above, I wrote down the equation of an ellipsoid, which is defining the position of a point on the surface. Point has the coordinates x, y, and z. That's a point on the surface of this ellipsoid. And A, B, C are the three axes of this ellipsoid. So with that equation, you define the geometry of this ellipsoid. And now we would like to look at the tip of our traction vector, and we would say this traction vector has the components x, y, and z. And in this case, we would say that this x value here, this is being introduced up here, right? And this is equal to the x component of the traction. And in the same way, the y would be put in here, and we would take the y component, and z would be put up into the equation on the top. Okay? Now we only have to calculate the components of the traction vector by taking the stress, which we assume we know. We assume that we have pi. We take the components of n in this coordinate system. You know, n has is of unit length, so it has the components defined with theta and phi in a spherical coordinate system. This would be the x component, y component, z component of n. And we're multiplying this into the matrix here, into the stress tensor, which we would prescribe in principal coordinates with the three stresses here. So that we would define the stress tensor in terms of pi 1, pi 2, pi 3. Value along here, along there, and along there. And we get now the x, y, and z components, and we put those into the equation for the ellipse. And that's what I'm doing down here. We would put x here, this tx, we put this value. Let me continue my drawing here. So I'm evaluating this tau x, and now I'm putting this into the equation up here, and it looks something like this. This is the top here. And when dividing this by the axis of the ellipsoid, by the main axis A, and the first axis is equivalent to the first principal stress, and we put this down here, and we divide as such. And by doing so, you can see that the three principal stresses are canceling here, pi 1, pi 2, pi 3. And then when working through the trigonometric relations, you will see that all of this is adding up to 1. And in this way, we can see that indeed the components of the traction tensor satisfy the equation of the ellipsoid. So, and that's the geometric meaning which I used for describing the stress. A special case now of the stress occurs in hydrostatics. We would look at a object submerged somewhere under, say, you're diving. If you go down 10 meters in water, you are exposed to an additional atmosphere. So we would look at an object submerged under a static fluid level, and the local pressure down here is equal to the pressure on top of the fluid level plus the hydrostatic level rho GH. So that's the local pressure. But what is the traction on the surface? The traction is acting normal to the surface. There's only a normal traction. There's no shear involved in the static case. And the magnitude is equal to minus P, minus the local pressure. And the minus sign comes from the sign convection where pressure is negative and tension would be positive. So whatever direction the surface has locally determines the direction of the traction, and the magnitude is given just by the local pressure. And the stress tensor in the vicinity here at the stress tensor at the depth h is just given by a spherical stress. It has the components minus p, and all the diagonals. And this would be independent of the coordinate system, whatever you choose. The stress ellipsoid has reduced to a spherical stress. It's a sphere which describes the stress. So in whatever direction you look at the stress tensor, you obviously will have the same value. And the spherical stress would be described as just the stress here is equal to minus the pressure times the unit vector. Okay. Conventionally, the stress which we just used for defining the traction all over is separated into two contributions. One is the pressure contribution, is an isotropic contribution. It would be a normal stress, which is the same in all directions, plus an extra stress, which defines the deviations from the spherical geometry, from the spherical stress. In many cases, we would take this P being minus 1/3 of the trace of the stress tensor. So that would be just an average normal stress acting on our system. And this one would be then the deviatoric part. This would be the extra stress. Now, the pressure or the isotropic part of the stress is associated with volume changes. Meaning that a compression of our material element would just change its density, but would not change its shape. It would not distort this element, it would just make it smaller or bigger. And the asymmetry here with the deviatoric stress would be associated with shape changes. Therefore, a strain which we calculate with our method, with a strain tensor, Cauchy tensor or finger tensor, would contain shape changes and volume changes, both of them. And we would have to separate that into the two components when writing constitutive equations. And that's done conventionally. That's the common procedure. And it's the source for a simplification of constitutive equations. As soon as we say that volume changes are negligible in our system, we have flow at constant volume, at constant density, then the stress is only associated with the shape changes. And we will formulate constitutive equations in terms of the deviatoric stress only, independent of the local stress level. And that eliminates really a whole area of physics. The volume changes are described in thermodynamics. Volume as a function of pressure and temperature. And if we say we have constant volume, we just neglect all thermodynamics, which is probably not appreciated by people working in thermodynamics. So, but it's a tremendous simplification. Just allows us to get solutions in fluid mechanics problems, and we have to be aware of that simplification. If we deal with problems at very, very high pressure, then like in injection molding, or when looking at processing at very high pressures, like in supercritical solutions, then we have to incorporate volume changes in our view. But at regular conditions, we would deal with constant density and neglect the volume changes in that system. So that's we will use that when writing constitutive equations. Another special situation for stresses occurs with the so-called plane stress, and that goes something like this. We have many applications where one principal axis is constant throughout the flow. This would be, as we describe the system, would be our third direction in the coordinate system would always be a principal direction for the stress. And then we can rotate our stress tensor or rotate our coordinate system around the third axis, and then we would get all kinds of values for the components here. We would get off-diagonal terms. But the principal stress would always stay the same. One common application for the plane stress is shear flow, where we have action in the one direction and two direction. One is the flow direction, and two is the gradient direction. Three is the neutral direction, and that's always a principal direction for the stress. And we would simplify our stress tensor in that format for describing shear flow. We could choose a planar extensional flow in which you would, say, stretch a material element in one direction, and it would shrink in the two direction, while you keep the third direction, the dimension in the third direction constant. You don't allow any size, any change in the third direction. You still have to apply a stress in the third direction. So the stress in the third direction is not zero. Also in shear flow, it's not zero. It's a finite value. But it's always a principal stress, and we are allowed to reduce the stress tensor into that format. And of course, shear flow and plan extension could be superimposed to have all kinds of arbitrary planar flows. The stress in plane flows have been described with a so-called Moore circle. And that's a nice geometric representation which goes something like follow. Just, I want you to get a flavor of the Moore circle. And again, I will use geometry for describing that. We will start out with a stress. We assume that we know the stress completely, and we can choose principal stress values P1, P2, P3, and we know the principal directions. So we know everything about the stress. And we will now consider a material plane, say, or we consider a surface in space. And locally, it will be a plane, of course, for a small area element, with a unit normal n. And we would like to know what's the stress on this surface. We would like to know what's the normal stress on that surface and what's the shear stress on that surface. And you know how to do that. You would calculate the traction and then divide it into a normal traction into shear traction. And let's do that. But now, in addition, I drew the other information which we have. We know the principal directions. This would be one principal direction, and this would be another principal direction, normal to that. This would be the axis of our stress ellipsoid at point P. And the third axis is coming out of this point. And when we choose the area, the inclination of this area, we always would maintain the third principal axis constant. And that's, so we were talking about a plane stress situation. Okay. Now, the inclination of n with respect to the first principal axis is alpha. So if alpha is equal to 0, the traction will be normal to the surface, but there will be a principal traction. And at alpha goes to 90 degrees, it also will be a principal traction again. Right? It will also be normal to that surface. Now here we just say calculated the components of the traction. This would be the traction vector given by the stress, and we decompose it in a normal and in a tangent contribution. And I wrote down the two contributions here in here. This is the normal pi nn. Pi nn means n dot pi dot n would be dotted on both sides. And this has these components, and we express it in the principal stress components, since that's how we started out with the stress tensor. And then this would be the shear stress on the surface, again defined with those two. And the tangent to alpha would be given as just a ratio of those two. And we are defining already some new variable, r. Now let's combine that in Moore's circle. He did this about 80 years ago or so. In fact, I found an old mechanics book once. It was out on a shelf, in university, when you go through the hallway, always have those eliminated books, and nobody wanted to have Moore's book anymore on mechanics. So I found this, I think of 1914 or so, nicely described in over many pages, the Moore circle, not using the tensor notation where everything goes pretty quickly. Okay, so Moore combined those two expressions where he had the normal component on his surface and the shear component and combined them into an equation, and this is really the equation of a circle which is displaced by some value x0, and x0 is just the average principal stress. Here, this is the principal stress. Let me go back to my drawing here. Here, we're talking about this plane, and we had a principal stress in one direction and a principal stress in two directions. So as alpha goes to 0, our normal stress is equal to this value, and the shear stress is equal to 0. As alpha increases, we have a smaller normal stress on the surface, and a shear stress is appearing. So we always can read off the normal stress and the shear stress on this graphic or thing. And as 2 alpha goes to 180, or alpha goes to 90 degrees, we have our normal here reaching the second principal direction, and we are having the second principal stress then, and no shear stress anymore. So in the absence of computers, and maybe also in the absence of training, you could give this graph to people who are for building bridges, for instance. You tell them about the stresses in certain situations, and they drew those circles, and they calculated the angle dependence of shear stresses and normal stresses in a convenient way. So this was more a historical excursion here in talking about Moore's circle. Now, we will look at the stress in shear flow and in extensional flow. So what's the matrix of the stress tensor in the specific coordinate system? Remember, we picked a specific coordinate system for shear flow, where the one direction was the flow direction, two direction the gradient direction, and three the neutral direction. And we will now write down the matrix of the stress tensor in this type of coordinate system. And you can see that we're already decomposing the stress. We have minus the pressure, local pressure, plus the normal stress in one direction, similar term in two directions, similar term in three directions, and then we have the shear stresses associated with that specific coordinate system, specific choice of coordinate system. So the shear coordinate system is not a principal coordinate system. We would have to describe it in some angle to the between flow direction and two direction. So it's not a principal coordinate system, but certainly the third direction is a principal direction. So you can see those terms are 0 in the matrix, and 3 is a principal direction. It's a plane stress, which we are going to look at. The quantities to measure now in an experiment would be the shear stress. Say we produce shear flow under some conditions, and we would like to define the stress completely. Now we would want to know the shear stress, and we would want to know the normal stress difference between here and here, and the normal stress difference between here and here, between those. And then we would like to know the pressure. But the pressure is eliminated from our viewpoint by saying that we have constant density. We have no way of calculating the pressure. So in real flow calculations, you will take the pressure somewhere at the boundary, and then you calculate normal stress differences throughout the flow field, and from that you get absolute values for the normal stress. So, but from the constitutive equation, we will have no information about the stresses. We own the value, the absolute value of the normal stresses. We only get the first normal stress and the second normal stress difference. In extensional flow, we also had a specific coordinate system that went along the 3 axes of stretching of that specific velocity profile. And in the case of extensional flow, the coordinate system is a principal coordinate system. The matrix of the stress tensor reduces to diagonal form. And again, we only would be able to describe the first normal stress difference or the second normal stress difference in our calculations in rheology when formulating constitutive equations. So those are the special cases. All together here, we will. This is the summary of the two. This is the two stress matrices for the two flows. And when talking about material functions, I will pull up this slide quite often together with the slide on the deformation gradient and the strain tensor, and then we will look at the relation between stress and strain. So by doing that, we use everything we talked about so far, but we use it in a very simple way. So it's mathematics will be very, very simple from here on. Especially tensor and vector analysis can be eliminated as soon as you grind through your algebra up to this point. And as long as you stay in simple flow geometries like shear and extension. When we go to more complicated geometries, then you have to introduce the tensorial notation. Now, you can choose a Cartesian coordinate system. I did that so far for all cases, and you can define now the stress tensor components on those different planes. This would be a y plane, this would be an x plane, and a z plane, and you have always one normal stress and two shear stresses on those planes. But when you work in a cylindrical coordinate system, you would have material elements which have different magnitude of the faces. Here this would be a large area and this would be a small area due to the curvature. So whenever you have curvature, those elements are somewhat asymmetric, and you have to account for that when writing down the force balance on material elements. That will give rise to additional terms and to some interesting phenomena. It's even more severe in a spherical coordinate system. This is just a segment from a sphere, and it's decreasing in size chronically as it goes towards the center of that coordinate system. In summary, now, what do we know about the stress? It's fully defined by a matrix, 3 by 3, which has 6 independent components. From that stress tensor, we can calculate the local traction. Wherever we know the stress tensor, we get the traction for whatever direction we are choosing for every n we would like to know. And this traction can be described by the stress ellipsoid. Symmetry, nice properties, splitting of the stress into an isotropic contribution and a deviatoric part will be used for writing constitutive equations, just to simplify the approach, and special cases where the spherical stress, where the stress ellipsoid reduces to a sphere, and the plane stress, where the third axis is also principal axis, but here we might be off diagonal. We can formulate more circle and the stress components, shear stress and normal stress on inclined surfaces. This concludes the definition of the strain and the stress. And maybe we should break here. Yeah, have a short break. Polymer Science 757, Lecture 5B. The next subject I wanted to discuss with you is the conservation of mass and of linear momentum. And you need those for formulating flow problems, for describing the motion of material elements. Now, for calculating those conservation equations, we will pick a volume element of finite size and of arbitrary shape. And this should be not an incremental volume element. This will be a large volume element, substantially large. And on this volume element, you will look at the surface. Say if this is a surface element, then this would have a normal n and a value ds for this surface element. We will use, this is a frame fixed in space. This volume element is fixed in space, and some fluid is allowed to flow into that system and come out of this volume element. And for solving the flow problem, we will use the Gauss theorem. Which goes something like this. You can take integral over the surface, which is a double integral of a quantity n dot, and this could be a scalar, or it could be a vector, or it could be a tensor, any of those. And this can be rewritten in terms of a volume integral, a triple integral, of the divergence, this is the Nabla operator, differential in space, of the same quantities, of some scalar, of some vector, and of some tensor. In the case of the scalar, this dot has no meaning. Also here, it would be just a unit normal times s would be meaningless. But the dot has an operational character when looking at the vector and also when looking at the tensor. So I left the dot in instead of, like you would, of course, write delta s in terms of a scalar, would be just the gradient of a scalar quantity. So this relation we will use for writing down the mass balance, the conservation of mass in a material element. Now, across the surface of our frame here, let me go back to this. Across the surface here, there is some flow coming out, so mass is leaving or entering if the velocity is negative in that system. And we can write a balance over the entire surface. So for writing those balances, we would like to know the flux going through specific areas. And in chemical engineering, there are many equations where the flux is being described. For instance, you could say the velocity, this is a little small, maybe Becky, if you could make this a little larger. Yes. The volume flux, this is the volume per unit area, is given by the velocity. That's actually what velocity is. It's volume per unit area. So if you multiply the velocity, if you project the velocity into the normal, that would be the normal component of the velocity to a surface area, and you multiply this with the surface area, then you have the total flux, or the amount of fluid per unit time going through the area element. Now, the mass flux would be given as rho times u. So if we project rho times u onto n, into the direction normal to the surface, and multiply with the surface area, we have the amount of mass per unit time and per unit area, or in this case, it's related to this area dA. And you could do a similar, you could derive similar expressions for the diffusive mass flux as J is related to the local concentration. This is used in mass transfer, and it's projected onto N. And again, this is the mass per unit time moving through dA. Or you could talk about heat flux, described by Fourier's law, and again, you have the similar relation. Now, Bird, Armstrong, and Hasegawa use the term momentum flux for the stress tensor because they can express the stress tensor also in terms of the stress projected onto N multiplied with dA. So this is really the traction, and this traction multiplied with the area dA is the force which is acting on this area element. So that's what we are going to use in writing those balance equations. The first subject is mass balance. We want to calculate the change of mass within this control volume, which I drew here on the blackboard. So this volume integral, this volume integral gives us the total mass in the frame, and the change of that mass per time, and it's an absolute differential because the frame is fixed in space, so the change in time is equal to the sum of all the mass flux in and out over the entire surface. So we do this over the surface integral. We replace the surface integral with, by using the Gauss theorem with a volume integral, using the local gradient, local velocity gradients in the system. And then we combine the two volume integrals into a single volume integral in which this term is subtracted from the other term. We moved, by the way, we moved this d dt inside. And by moving it inside, we would have d dt as a local time derivative. So in this case, it will be a partial time derivative. It's meant for the local change of density within our volume element. So partial derivative of the density plus, here there was a minus sign up here involved because the unit normal we used is pointing outward. So whenever this flux is positive, it means mass is leaving the system. So that's where the negative sign comes. So it will come over with a positive sign here, and the whole integral is equal to 0. Now, the choice of volume element is arbitrary. It can have any shape, any size. And we can now pick any small or big volume, and still this integral should hold. That means that the integral is only equal to 0 if the kernel is equal to 0. So if this equation holds for arbitrary volume elements, arbitrary frames in space, then the kernel is equal to 0, and we can write this directly. And this is the equation for conservation of mass, which is used in tabulated form and which we can use in the book in solving flow problems. If we take a constant density now, if we simplify the problem, we could say, well, the density is constant. This term drops out. Density is constant, goes outside here, and this term is equal to 0. So the expression reduces to the divergence of the velocity equal to 0. And when in flows at constant density, we will use this expression for describing constant density. That's the equivalent. Divergence of the velocity equal to 0 in all cases. The next equation which we need would be for the conservation of linear momentum. There's linear momentum entering our volume element just by convection. The fluid which enters the control volume might have some velocity. So there's some kinetic energy involved with this fluid entering. Let's say if you have slowly moving liquid entering and fast moving liquid leaving your control volume, then you are losing momentum. So the linear momentum of the material in your control volume will decay in time. So we have to write down a balance of the linear momentum within the volume element. So if this is the linear momentum, rho times u, per unit volume, integrated over the whole volume element. That will give us the total linear momentum. I just wrote down Lm for linear momentum for the mass of material inside our volume. The time derivative, again, gives the rate of change of that linear momentum. And that's equal to whatever is entering and leaving our system. The term leaving here is given, for instance, by momentum flux. This is the momentum flux projected onto the normal vector n and integrated over the surface area and having a minus sign because that would be the momentum flux leaving. N is pointing outward of our system. Now, the stress will give rise to some traction on the surface, n times pi, and this traction will accelerate or decelerate the liquid in our control volume and will therefore change the momentum. It will add to this contribution. We have to integrate the traction over the entire surface area to get this contribution. And then there might be some body forces, individual material elements in our control volume. You know, we have a large control volume here, so individual material element might be accelerated or decelerated or affected by some volume forces. This could be gravity, as I put it down here with G, but you could have some magnetic field effects or some other contributions which give rise to a volume force. And those volume forces will change the linear momentum of the system, and they have to be integrated over the entire volume, and they will give a contribution to our balance here. Now, again, the surface integrals, the double integrals, those two, will be converted into volume integrals, and they're already written in a form where we have n dot. See on the blackboard here, in Gauss' theorem is easy to remember because you only replace n dot in the surface integral with nabla dot in the volume integral, and then you can write it down immediately. Therefore, when writing down those surface integrals, we always write n dot pi there, not pi dot n, because then we would have to rearrange it. And then we go to the volume integral, and down here is the volume integral having the left side term combined with the right side terms here equal to 0. And again, the choice of our volume element was arbitrary. The kernel has to be equal to 0, otherwise it would not satisfy this equation for arbitrary geometries. So we can write this equation and say this is equal to 0. Unconventionally, the acceleration terms are on the left side, or inertial terms, and on the right side is the stress contribution and the body forces, here gravity. That's the conventional way of writing that. Now, from here on, you could change this equation even further. So what do people do when you look in books, in fluid mechanics books? For instance, they take this term here, which is basically a differential in space, ddx, ddy, ddz. That's the nabla operator. Okay? They take this differential and they introduce differentiation by parts for this term. And then they have nabla dot rho u as one of the terms. And one of the u's would be outside. And this term can be replaced with conservation of mass, as we had before. And then everything simplifies. Some terms are dropping out. So you can rearrange when doing this. Yeah. And also integration, differentiation by parts then also changes some of that. And the second change in notation which you will find is that the stress tensor pi will be split into pressure contribution, isotopic contribution, and the deviatoric part. So this will be nabla dot p. Pressure is a scalar quantity, so the dot has no meaning in this case, would be just the pressure gradient, plus the gradient of the stress would be nabla dot tau, the deviatoric. So those types of variations you will find in books, and that's okay. And I brought some books here for which you could use. For instance, here Bird, Armstrong, and Hasager in very much in the back here has the tabulated form of the stress equation of motion. Here you have all the components in rectangular, in cylindrical, in spherical coordinates. And then you don't have to grind through the details. And the advantage of this is that you can use the scalar algebra when solving equations like that. Okay, so in the back at page 612, for instance, you see components. And Bird's books are especially nice, also transport phenomena for looking up those tabulated equations of conservation of linear momentum, and also of energy. I won't talk about the energy because we will not discuss the non-isothermal flow problems in detail. We will talk about non-isothermal rheology, but we will not solve non-isothermal flow problems. Okay, so conservation of mass and linear momentum is sufficient for us fast in the moment. How about conservation of angular momentum? We looked at this already. The conservation of angular momentum resulted in the symmetric stress tensor. So that is already satisfied when writing down the stress components. So with those tools now we can go back to rheology and we can start looking at constitutive equations. Larsen has a very nice description of constitutive equation approach, how to model a material and how to distinguish between molecular models and continuous models for the stress. So I recommend at this part of the class to look at Larsen's book and at least read some introductory part in that. It's very helpful. I have a copy if you want to borrow that from me, and maybe if you want to switch this around. It's also worth getting, I think. So when writing constitutive equations, we would like to describe the stress of a flowing material. In our case, the stress of a flowing polymeric material. And there are two basically different approaches. One is the molecular approach, where the molecular motion is somehow described in some approximation. A model for the molecular motion is proposed, and from the forces on the molecule, then a macroscopic stress is being derived. That's a subject of molecular dynamics, for instance. Not only molecular aspects should be considered, there are materials which have some supramolecular structures which also give rise to stress, and that should be incorporated. For instance, in a block copolymer, in a polymer blend, when you have some interfaces coming into the material, then they have to be incorporated into the theoretical approach, and that will be used then to describe the stress. And then we need a model also for the relating the molecular motion to the macroscopic motion of the material somehow. So basically the molecular dynamics approach links the molecular motion to the macroscopic phenomena which are observed in macromolecular materials. The second approach is a continuum approach, where we would like to predict the stress from a strain history of a material. Now, those models are basically derived in the following way. Some simple relation is proposed. You have maybe a splendid idea how the stress might depend on the strain history. And then you use that formalism, that idea, and calculate startup of shear flow or startup or extension of flow or any transient experiments in polymeric materials, and predict the stress in those experiments. Or maybe you select some additional I don't know, you have some microphone problems, I don't know. Or you maybe prescribe the stress in the material and you predict the flow in that system, and then you check your prediction against the experimental observation, and if there's an agreement, then you praise your equation. You probably give your name to it. You know, a good rheologist has always his own equation to describe their own consistent equation and advertise it in meetings. So there's a lot of emotion and preferences involved. But the hard facts are always there. There's always the prediction, which everybody should be able to follow in a derivation on the paper, and the experimental observation. Now, if there's disagreement between the prediction and the experiment, it might as well be that the theory is okay and the experiment is horrible. And that was the case for a long time. We just didn't get good data to maybe extensional flow in polymeric liquids or startups in shear flow of a polymeric liquid. The information was very limited. And one of the most successful equations nowadays, an integral constitutive equation, which describes those phenomena very well, has been checked early on and has been found useless because there was no agreement. And the reason that there was no agreement was that the data were just too bad. But in the meantime, the advancement in rheometers is so far that the data are very reliable, and we really can check the theories, the prediction of models very, very nicely. So, okay, so in this approach here, when deriving continuum models, we need a rheometry. We need the measurements in well-defined theories to test the model. Secondly, we will use the rheometry to determine the material parameters in the model. And certainly we might do some experiments where we, say, look at the stress in specific situations and find the anisotropy of the material. This anisotropy would be associated with molecular anisotropy of the material. It would relate to birefringence, for instance. So rheometry can look at many different aspects of the rheological behavior. The application of those continuum models is in polymer processing, where we would like to know forces and flow rates, for instance, and also in solid mechanics. So you produce a polymeric part and you would like to know the load limitations, or you would like to know the deflection of that part. That also would be described in a constitutive equation for solid in this case. So for processing here, we would use a liquid constitutive equation, and for the solid, we would use some specific equation which describes solid behavior. Now, limiting behaviors, typical of those constitutive equations, are the Newtonian liquid for low molecular weight materials, low molecular weight liquids. The only parameter is the viscosity. In there, the stress is proportional to the rate of deformation. Coefficient is the viscosity. Density changes are not mentioned here, but you could formulate an equation for a compressible Newtonian liquid. Note that I already took the deviatoric stress to describe this Newtonian behavior. The other case is the other extreme is the Hookean solid, which is characterized by a modulus G, and in this case the deviatoric stress is given by the strain between the stress-free state, indicated as T0, and the current state T. So now you already can use the finger strain tensor or Cauchy strain tensor, which we discussed, and formulate a very simple constitutive equation. Right? You just take the deviatoric stress and proportional to the strain between stress-free state and the current state, multiplied with the modulus, and that's the only coefficient which enters here. It turns out that for viscoelastic materials, there is a very simple equation for the behavior at the transition from liquid to solid. you could, for instance, look at a cross-linking polymer, maybe or at an epoxy, which in the beginning, when the reaction has not even started, is low molecular weight, which tells you it's a Newtonian liquid in the beginning. And then you react this material to completion. All molecules are connected to each other. It's basically one macromolecule which you have as a result. And it behaves Hookean at the end. And at the transition from liquid to solid, there is a so-called critical state which reduces the behavior also to a simple limiting behavior. And that's the so-called critical gel behavior. And this is described here. We have to go into linear viscoelasticity to describe that. But this is on an equal footing to those other behaviors. Yeah. Now, when writing constitutive equations, we have to introduce some general assumptions. We have to follow some rules. So when you make your guess, you want to formulate a relation between stress and strain. And then you have to follow those specific rules here. Three specific rules. The first one is the principle of local action. And that says that the stress in a material element depends only on the strain history of that specific material element. It is independent of the history of a material element which is neighboring. Now, that's a very important assumption. It means that you can formulate your constitutive equations for homogeneous flows in the same way as you can formulate your constitutive equation for inhomogeneous flows. Note, in an inhomogeneous flow, you would have a rate of deformation as a function of position. So your material element of interest might be subjected to a higher rate of deformation than the neighboring element. And then some gradients are coming up in the flow. And those gradients are assumed to be negligible when formulating an equation for the stress. Now, this is the so-called simple fluid assumption. For all fluids which behave like that are called simple fluids. And there has not been found a case where this simple fluid assumption has been contradicted. The second assumption he is introduced is the principle of fading memory. And that simply says that the influence of a deformation on the stress decays in time. So the longer this deformation is back in the past, the smaller its contribution to the stress tensor. The material has a so-called decaying memory. And the third principle, which we are looking, is the so-called principle of frame invariance, which says that the stress does not change when you change your frame of reference. And let me exemplify this with an example from Larsen's book here. Larsen has a nice example where he took a material element and rotated this element by some angle theta. And he wrote down the stress in the material like this and assumed, say, that this is a solid. Now, what would be the most simple constitutive equation for a solid? It would be, say, the stress being proportional to the deformation gradient. See, deformation gradient describes the stretching of lines, changing of angles. So you could say the stress is a function of the deformation gradient, and he followed up on that. He would say the stress is a function, in say, in this case, inverse of the deformation gradient. And for the rotation, which Larsen picked here, the deformation gradient is given by a rotation matrix as such. So we would have the stress equal to the deformation this matrix here, multiplied with a coefficient of proportionality, which would be some modulus. And now note that if this equation is true, then the stress would be 0 at 0 angle. Everything would be would be reduced to a diagonal, would have just ones here, would be just an isotropic stress, no extra stress involved. But the stress components change as the angle theta of this rotation changes. So the conclusion from that, or the prediction from that constitutive equation, is that when you rotate a piece of material by some angle, you introduce some stress. And that clearly is wrong. Right? This would violate the experimental observation. A equally simple guess would be now a replacement in this constitutive equation, replacement of the deformation gradient with the strain gradient, with a strain tensor here. This is this finger strain tensor which you used. So we could say that the stress is equal to the modulus times the finger strain tensor. And when you calculate the finger strain tensor components, when you just calculate this when you evaluate this product here for this matrix, then you will find that this matrix is equal to the unit matrix at all angles theta. So a simple rotation will not introduce any stress in the system. Therefore, the formulation of constitutive equations with the finger strain tensor or equally with the Cauchy strain tensor is okay. If you just use the deformation gradient, you would violate the third principle here, the principle of frame invariance. This concludes everything I want to discuss on the basics. There was the introduction into, say, the tools which we need for rheology. Next time we will start talking about the material functions, about experiments, about experimental results from rheometers in shear and extension. We will apply what we just defined so far.